because I'm trying to get the second year students of Norwegian ones to get to see all of the subsea gear that I brought along. So it will be like a 20-minute break today also, like we did yesterday. Did you have fun yesterday at the PRS base? Yeah. It was pretty awesome seeing just how big stuff is when you get to actually. It's one thing looking at the screen here and just, well, you don't really know how big that ship is and everything like that, but then you get to see it and whoa, it's an eye-opener when you get to see it. So you suddenly start to realize why it's so important to have enough space on deck on your ship, because stuff is just so huge when you start using equipment like this. So it's really, really fun to see it. We had come as far as starting to look at health, safety, and environment regulations. So we have a little bit more to look at with regards to regulations and stuff, and then we'll start looking at more risk analysis and how that is done in the industry. And that's a fairly important part, so it's nice to get a brief walkthrough of that. But that's more like the HSE engineers. They get quite a lot of education in that part. So Frederick knows everything about it. So actually it was Frederick that should have this this part of the course, but so we have framework regulations, which sort of set the basis for everything. It gives everything a framework to work within with regards to health, safety, and environment, because there will always be certain stuff in the regulations that will be the same no matter where you are. So those are sort of the frameworks that give you the basis of how it's going to work. And it's with regard to being a comprehensible and justifiable business, for an example. That's a framework. So all of the businesses have to act in a certain way in order to be in compliance with the framework. We also have management regulations, which set requirements to the management of risks, of strategy, and also monitoring and control of the business, so that with regards to the risk management, that's where the next part comes in, where we do risk analysis to try to figure out what could go wrong and how could it go wrong. There are also technical and operational regulations with regards to more the health of the workers, the environment that they're working in, that it's going to be conducive to their health and not detrimental to their health, and also safety at land-based facilities. We also have facility regulations, and you remember sort of the last thing we looked at on Tuesday was that a facility, that's more like a rig or an FPSO, so a floating vessel that's just stuck there, immobilized, because it's always there doing work, while a vessel is one that's scooting about and doing work in several places. So for facilities, we have specific requirements to the design and layout of them, and equipment and safety barriers and stuff like that. You could see some of it when we were at the PRS base yesterday. For an example, when we were walking in stairs, there were quite a lot of signs put up that use the handrails when you're walking in the stairs. So that's typical of HSE requirements for offshore and stuff like that. Because one thing is walking in the stairs at the PRS base. The ground isn't going to start to move underneath you. We're not in an earthquake zone, so there's not really much chance of you falling unless you actually trip on your own feet while you're walking down there. So, but still, if you trip, you would save yourself if you were holding the handrails. But when you're out offshore on a rig or on a vessel, everything is moving. So you could suddenly hit a wave and get the real jolt through the entire vessel or rig just as you're walking down the stairs, and that could cause quite serious accidents. So that's why they are very, very strict about using the handrails when you're offshore, because you're always to have at least one hand on your handrails. Preferably, you're going to have both of them, because then you're really safe. So it's and it sounds sort of trivial just thinking about such a minor thing, but it has actually caused quite a significant dip in injuries offshore. Just the fact that they're holding onto the handrails when they're walking in stairs. So a lot of sprained ankles and stuff like that have been avoided because of it. So it's basically it is for the health of the workers, but it is also set in as a requirement to how you design it, that all of the stairs and ladders and stuff, everything has handrails. So it's a part of the design requirement. You have to have handrails that are easy to be reached. And that's just one example. There are other safety barriers also. For an example is if you're doing some sort of dangerous work, whether it is hot work, welding or something similar, or if it's just lifting or anything like that, you will set up safety barriers. Like when we're looking at the divers welding habitat yesterday, you could see that when we were coming in and looking into the welding habitat, behind us there was a warded off section, and that was because they were doing lifts there. So no one was allowed to go past that sectioned off grid there, because if you walked in there, we would have to have been a part of that lifting crew, and we would have had hard hats and everything in order, and know what they were doing with regards to lifting, just in case something fell down. So that's one other example of safety barriers taken into account, just how you design and lay out your facility with regards to safety there. There are also activity regulations, and this goes more for how you plan everything, and the environment, emissions, the maintenance, monitoring. Right. We'll be doing a slightly longer break today also, because I'm trying to get the second year students of Norwegian ones to get to see all of the subsea gear that I brought along. So it will be like a 20-minute break today also, like we did yesterday. Did you have fun yesterday at the PRS base? Yeah. It was pretty awesome seeing just how big stuff is when you get to actually. It's one thing looking at the screen here and just, well, you don't really know how big that ship is and everything like that, but then you get to see it and whoa, it's an eye-opener when you get to see it. So you suddenly start to realize why it's so important to have enough space on deck on your ship, because stuff is just so huge when you start using equipment like this. So it's really, really fun to see it. We had come as far as starting to look at health, safety, and environment regulations. So we have a little bit more to look at with regards to regulations and stuff, and then we'll start looking at more risk analysis and how that is done in the industry. And that's a fairly important part. So it's nice to get a brief walkthrough of that. But that's more like the HSE engineers. They get quite a lot of education in that part. So Frederick knows everything about it. So actually, it was Frederick that should have this this part of the course. But so we have framework regulations, which sort of set the basis for everything. It gives everything a framework to work within with regards to health, safety, and environment, because there will always be certain stuff in the regulations that will be the same no matter where you are. So those are sort of the frameworks that give you the basis of how it's going to work. And it's with regard to being a comprehensible and justifiable business, for an example. That's a framework. So all of the businesses have to act in a certain way in order to be in compliance with the framework. We also have management regulations, which set requirements to the management of risks, of strategy, and also monitoring and control of the business. So that with regards to the risk management, that's where the next part comes in, where we do risk analysis to try to figure out what could go wrong and how could it go wrong. There are also technical and operational regulations with regards to more the health of the workers, the environment that they're working in, that it's going to be conducive to their health and not detrimental to their health, and also safety at land-based facilities. We also have facility regulations, and you remember sort of the last thing we looked at on Tuesday was that a facility, that's more like a rig or an FPSO, so a floating vessel that's just stuck there, immobilized, because it's always there doing work, while a vessel is one that's scooting about and doing work in several places. So for facilities, we have specific requirements to the design and layout of them, and equipment and safety barriers and stuff like that. You could see some of it when we were at the PRS base yesterday. For an example, when we were walking in stairs, there were quite a lot of signs put up that use the handrails when you're walking in the stairs. So that's typical of HSE requirements for offshore and stuff like that. Because one thing is walking in the stairs at the PRS base. The ground isn't going to start to move underneath you. We're not in an earthquake zone, so there's not really much chance of you falling unless you actually trip on your own feet while you're walking down there. So, but still, if you trip, you would save yourself if you were holding the handrails. But when you're out offshore on a rig or on a vessel, everything is moving. So you could suddenly hit a wave and get a real jolt through the entire vessel or rig just as you're walking down the stairs, and that could cause quite serious accidents. So that's why they are very, very strict about using the handrails when you're offshore, because you're always to have at least one hand on your handrails. Preferably, you're going to have both of them, because then you are really safe. So it's and it sounds sort of trivial just thinking about such a minor thing, but it has actually caused quite a significant dip in injuries offshore. Just the fact that they're holding onto the handrails when they're walking in stairs. So a lot of sprained ankles and stuff like that have been avoided because of it. So it's basically it is for the health of the workers, but it is also set in as a requirement to how you design it, that all of the stairs and ladders and stuff, everything has handrails. So it's a part of the design requirement. You have to have handrails that are easy to be reached. And that's just one example. There are other safety barriers also. For an example, is if you're doing some sort of dangerous work, whether it is hot work, welding or something similar, or if it's just lifting or anything like that, you will set up safety barriers. Like when we're looking at the divers welding habitat yesterday, you could see that when we were coming in and looking into the welding habitat, behind us there was a warded off section, and that was because they were doing lifts there. So no one was allowed to go past that sectioned off grid there, because if you walked in there, we would have to have been a part of that lifting crew, and we would have had hard hats and everything in order, and know what they were doing with regards to lifting, just in case something fell down. So that's one other example of safety barriers taken into account, just how you design and lay out your facility with regards to safety there. There are also activity regulations, and this goes more for how you plan everything, and the environment, emissions, the maintenance, monitoring, readiness, such as the PRS base is also readiness for if anything happens with all of these thousands of kilometers of pipeline. And also training and rehearsals, and that was also something they do at the PRS base. So if you remember, he talked about it all the way at the beginning of the presentation, that they are a readiness facility, so they are ready in case something happens, but they also need to be able to do what they need to do when something happens. So they are constantly training. They're even doing rehearsals, land-based rehearsals. That was some of the stuff that they were doing inside that we were watching. They were doing tests, so testing the equipment, that everything works, and also testing the personnel, that they know how to operate the equipment. And more of the training part is when they take on more commercial missions, so that they actually get a planned mission, like the retrofit T that they're going to do in 2017. That's a planned mission. So that's not a readiness where they just have to go out and fix something. It's a planned one, but they use it in order to train for the readiness stuff. So it's very important to have all of this in place. We also have particular regulations for the work environment in the Norwegian sector. So there we have under organization, management and participation regulation. There are quite strict requirements to risk assessment, training, information planning, and facilitation of work, both before the activity starts and while it's being performed. So what this sort of takes into account is that you can't just send off all of the people offshore to do a job that they've never done before. You need to train them, and you need to inform them about everything that's going to be done. So they do quite a lot of training on land before they go out offshore. If it is something that they've done before, several times, on several occasions, whether if it's, for an example, a lowering down a module, and this vessel has done this hundreds of times before, and the crew is fairly experienced, they won't do all that much training because they know what they're going to do. They're just going to refresh a little bit to make sure that everyone is on the same page, that no one has forgotten anything, and then they can be off. If it's a fairly fresh crew and a fairly new ship, then they would probably do quite a lot more training just to be sure that everyone knows what they're supposed to do. And also that also comes in under the planning part. So they have to really plan for all of this. So they have to take into account that we need time to train before we start the operation itself. It's also something that needs to be done, and the training itself also needs to be planned, of course. There are workplace regulations, which also have their own requirements to the design and layout, just as the health, safety, and environment have. Some of these regulations, workplace regulations, and the health, safety, and environment go sort of hand in hand. They sort of talk about the same stuff, but it's a little bit different how they act upon it. Administrative arrangements. There's quite a lot about having a company health service. So this is really important when you're offshore, that you actually have health personnel that can handle stuff. If someone gets sick or injured or anything, that you have competent personnel that can handle it. But it also counts even for a land-based industry. So even the school here has to have a company health service. So that if I've got an issue with my back, so that I'm hurting in my back when I'm sitting at my desk and working with the computer, I can have the company health service come in and look at my work situation, see if there is are there any improvements that we can do. Could we switch out your chair with a better one? Would that fix your back? Maybe you need a desk that can be raised up so that you can stand while you're working, because it's better for your back to be standing than sitting down. And they can look at stuff like that, and that's really important to have in offshore business also. We also need regional safety representatives, safety training, and competent enterprise. So that means that we have dedicated personnel. So for the school, it's actually Helen that is the safety representative. And that means that every now and then, I think it's twice a year or something like that, they have an inspection where they go through all of the school and they check that everything is in order in accordance with all of the workplace regulations and stuff like that. So she and a couple of other safety representatives will walk around and check everything. And they can actually put down a report afterwards. If they find something that's not in accordance with the regulations, they can put down a report and they can deliver it to the school administration. And then something has to be done about it. They can't just ignore it and say, oh, well, we're not going to do anything about that. They really have to do something about it. It's a part of the workplace regulation. And the same is offshore. They also have safety representatives that walk around, so that are apart from the health, safety, and environment crew, so that they usually work very closely to them, but they are two different instances, so that you sort of get a double checking of stuff, and that's really good to have, because sometimes the health, safety, and environment personnel, they might have missed something, they didn't see it, but then the safety representative comes around and they go, oh, there's something, you've missed that one, we have to do something about that. So it's a nice precaution to have, especially when you're offshore, where if something goes wrong, it can go so terribly wrong also. There are measures and limits regulation, and that's with regards to measuring noise, vibration, radiation, and chemicals, and also setting limits as to what are the limits that are allowed in a workplace. For example, my wife is a dentist, so they do x-rays. So they have radiation measurements and limitations with there. Of course, they have a separate room where the x-rays are being done, that has a lead lining in the walls, so that there is no radiation escaping that room. But there are quite a lot of regulations with regards to her not being in the doorway when the radiation is being done, when the x-ray is being done in there. So there are very important to have. So radiation isn't all that common when you're working as an engineer, but as soon as you start doing some NDT work, there might be x-rays being done there. And then it's really important to keep people away. So when I was working at at the processing plant at Kolsnes outside of Bergen. They were doing quite a lot of NDT because we were upgrading the entire plant. So I was working for Able, who was working for Statoil on Kolsnes. And Able was upgrading the entire plant, which meant that they were installing quite a lot of new pipes and welding and doing stuff there. So after every weld, they had to do NDTs, and they did X-rays. So what was done there was that whenever they were going to do NDTs, they were doing NDTs at night. So it was the night shift that was doing NDTs. And basically, more or less, all of the other night shifts were off for that night, because they wanted no people in the area when they were doing the X-rays. They wanted only the people that were qualified and competent to work with it and knew how to shield themselves from the radiation. So that's one of the important parts of how to do this. What you're most likely going to come up against is noise, vibration, and chemicals. It's very common to, at least noise and vibration is almost impossible to avoid in an industrial work site. Chemicals can be avoided, but usually some chemicals are present, so it's nice to know about those also. There's quite a lot of regulations to them. With noise, recent research has shown actually that it's not the very loud noises that's the big problem. So if you hear a big bang and stuff, you might have an irritating noise in your ear afterwards and have problem hearing for a little while. But that's not going to cause lasting damage in your ear unless it's really, really loud, like louder than a jet engine on an airplane or something like that. But it's actually the low constant noise that's the real problem. So for an example, I know they have quite a lot of problem with hearing when they're working in kindergartens, just because the noise isn't necessarily all that loud, but it's constant during the entire workday. There's always a lot of talking and screaming from the kids and stuff like that. So it's not classified as being too loud, but it's still, so long as it's constant, it's sort of slowly wearing down your ears so that your hearing gets worse. So that's something also to take into account. So always use your ear protectors when there is noise around. So and usually when you're offshore, you're more or less always required to wear a hard hat. And usually on the hard hat you will have your hearing protectors, so it's very easy to put them on when you need. Most of the hearing protectors when you're offshore also have microphones, so that they easily pick up, for an example, the person next to you talking. So they're going to allow that sound coming through, and they're going to play it on basically just headphones inside the ear protectors. But a loud noise, as soon as the microphone picks up a loud noise, it just blocks out everything. So it just shuts down, and then it's just a regular ear protector. So that's a really good system to have. I've had it quite a lot when I've worked in workshops myself, and it's amazing how good those microphones are to just blocking out the bad noise and letting conversations pass. So it's a very good tool to have. There are regulations for work execution, and with regards to the equipment that's going to be used and the requirements of the equipment, the technical parts of it, how you're going to use it. There are manufacturer regulations. If you're manufacturing anything that's going to be used, whether it's going to be imported or if it's a local market product, they're all covered by the regulations. But the manufacturer regulation is for the manufacturer. It's not for the employer of whoever is going to use the equipment that has been manufactured. So it's a sort of a separate one. It's not for the workplace per se. It's for the guys that are manufacturing it. So for an example, in Imenco's case, they would be covered by the manufacturer regulation when they are creating subsea equipment. Even though it's not Imenco that is operating it, they're the ones that are manufacturing it, so they have to follow the manufacturer regulations. One of those is the one that I referred to in the team project, where you could look for safety factors to use. So the machine directive from the European Union. So just tells quite a lot of how stuff is going to be made and designed, for that matter. Internal controls is something that is used to try to keep track of all of this, that everything is being used correctly and done correctly. So we have an example here where the work environment law sets a limit for how much overtime each worker is allowed to work within a certain time period. So for an example, for 1 week, you are allowed to work this many hours of overtime. But if you work more than that, it's starting to be detrimental to your focus and your attention, so that you won't be 100% when you're at work. So depending on what kind of work you have, the overtime rules can be very strict. And for an example, with a surgeon or stuff like that, they can have long shifts, but they are definitely not allowed to do overtime after those shifts. So they have to stop once their shift stops, because then they've sort of said that a regular person will be not be able to have full attention then. And if you're going to do surgery on someone, you really want them to have full attention when they're doing it. And the companies are required to have their own internal systems that control this. So it's not necessarily a supervisor from the government that comes in and keeps an eye on everything at all times. They do come in and do sort of inspections, and they are usually not announced. So they just suddenly show up and they're going to do an inspection of your internal control system. So that's how they sort of keep everyone in check in doing this. And that internal system, it needs to register the overtime for each of the employees, and it has to be able to give notice if that employee is exceeding the limit. So that not only is it to give notice to that employee that, well, you have to stop now, you're working too much overtime, but it also needs to give notice to the administration and whoever is in charge of this employee, so that they also know that, oh, I can't set him to do this task on overtime because I've already forced him to work too much overtime. So I'll have to put this task to someone else instead. And the same goes for other areas. So noise monitoring, those are also supposed to be internal control systems. So they log whenever they do noise monitoring act. So usually it's the safety representative like that goes around and measures the noise levels in the different rooms, just to check that everything is in order. But then there will be unannounced inspections that will check the logs just to see that everything is okay. And also for the company health service, you also have internal controls there and many other stuff. So almost everything that is regulated, you're supposed to have internal controls for. And the internal controls, they need to follow up the work environment law, the pollution law, the fire and explosion law, which is very important when we're offshore, the product control law, and the civil defense law, and electrical facilities and equipment law. So the electrical and equipment law is very closely related to fire and explosion. So these are the ones that are the most important. In many of these laws and regulations, they have specific requirements that you have to have an internal control system for this. So you can't sort of avoid it in any way. And the internal controls are there in order to ensure that the responsibility and the authority and also the communication lines are clearly defined and understood. So they have to make sure that everyone knows who they're going to go see if something goes wrong. And that's something that's very sort of focus on with the communication lines, so that we don't want a deck worker on a vessel to go directly to the captain if he sees a minor flaw or something in an equipment. That's not a point, because the captain has more than enough on his plate, so he doesn't need to be bogged down with all of the minor stuff. The deck personnel is supposed to go to his foreman or next leader or whatever it is. So following the communication lines of reporting stuff is very important. But of course, every now and then you will have breaks in your communication lines where someone that is lower down on the communication line realizes that, well, I'm reporting this stuff, and this is a clear violation of regulations. We have to do something about this for the good of the company, so that we don't get, if an inspection comes now, they're going to really be hard on us about this. And if he's reporting it and nothing happens, then he of course has to skip one point in the communication line and go further up in the system. But usually the communication lines work as they are supposed to work, so that you at least have to give it a try before you skip to the next level. And the internal controls also ensure that it is competent personnel that is used during construction, fabrication, installation, and operation. And that means basically that it is they're using people that either have experience enough or that they are educated enough to do this. So, for an example, during fabrication, you would want someone who was a what's it called again? You would want the workers that are doing the fabrication to have their papers in order, that they've actually gone through school and they've been apprentices. They've got all of the. It escapes me what they're certified. There was the correct word. So that they're certified workers in their field. That's one of the things that you want to make sure of. And one of the internal controls there is just as simple as keeping a record of the CVs and testimonies of all of the employees, just making sure that everyone has the papers that they claim to have. They're also to ensure that necessary training is given. For an example, with Statoil, there is usually always a health, safety, and environment course that is given for new employees. It depends a bit on exactly where in the Statoil system you are being employed. If it's a course that is just a couple of hours, or if it's a full day, or maybe it's a full week. Depends a bit on how dangerous the job you're going to do for Statoil is. And that course is, they're actually so stringent on doing these HSE courses that even when I was doing my vocational education to become a certified mechanic, I was sort of for a full week. I was over at the Hydro plant doing work there for them as a sort of exercise before I became an apprentice. And then I had to go through a full day of HSE course. I was supposed to be there for 1 week, but I had to do one extra day for the HSE course, so that I had that in place before they allowed me to start doing work inside the plant. Just because they're so stringent on the internal controls system, so they couldn't allow the system to just let anyone pass like that. They had to, even though I wasn't exactly allowed to work by myself. I always had to work alongside an experienced mechanic while I was there, because of course I was still in school. I wasn't even an apprentice yet. But still, I had to go through this entire HSE process. The internal control makes sure that a readiness system is established. So, for an example, on a rig offshore, readiness system is, for an example, fire readiness. In case of fire, who does what? Who is going to try to put out the fire? Who is going to make sure that everyone is evacuated? So make sure that system is both established and maintained, so that everyone knows what to do. And also have evaluations of the safety, and especially when you are modifying something. So when you have something that is supposed to, some sort of equipment that's supposed to do one type of work, and then you're modifying it to do another task, then it's very important to have internal controls in place to make sure that everything is done correctly and that it's going to be performing correctly. They also make sure that the work environment law is upheld with all the monitoring and work overtime, everything like that. And routines for document control. That's something that you're going to see quite a lot of, document control in the oil and gas industry. Basically, all companies that are working in the oil and gas industry usually have a fairly large documentation control section. So those are technically adept people that are just checking that everyone else has done all of their paperwork. That's basically what they're doing. And if some of the paperwork is incorrect or hasn't been properly filled out, or maybe has been filled out in the wrong manner or anything like that, they have to make sure that it is corrected. So they have to go to the person in charge and make sure that this needs to be fixed, because these papers need to be in order. And quite often, the people working in document control might have like a mechanical engineer degree as their baseline for education. They might also just have quite a lot of work experience in doing it, or they might have many courses that have given them the proper education and experience to do this. Internal controls also make sure that deliveries are done properly, so that you both get the quality that you're supposed to get when you're getting this delivery, and also that you get the documents that you're supposed to get. So, for an example, with Emenco, most of the gear Emenco produce is made out of some sort of metal. So it's not always steel, it might be titanium or it might be something else. And then you have certificates from the foundry. So the place where the metal was created, basically, before it was fabricated or anything like that. We have certificates from them just to show what is the percentages of everything that's in here, especially when you have alloys and stuff. You want to know the exact percentages of all of the chromium or nickel or whatever it is that you have added to your steel. You have test reports to give you the tensile strength and the yield strength of the material. So you want to know all of this, and shear strength of the material also, because when you get a material from a foundry, the foundry has created it according to a standard, and the standard gives the minimum of the strengths. So in order for it to be an S235 steel material, for example, it needs to have a minimum yield strength of 235 megapascals. But that doesn't mean that it can't have more. So in the test report from the foundry, it might say that it has 270 megapascals in yield strength. And it's sort of important to know that exactly what it is, because when you're getting into very specialized designs where you are into really special materials, very high strength steels and stuff like that, you're talking about megapascals limit that are up to 1,000, 1,200 in yield or tensile strength. Then you're talking about equipment that can become very brittle and stuff. So you want to know, what is the hardness of this? How are we liable to have this just shatter completely if it's strained too much? Not that it's going to start elongating itself and plastically be deformed before it breaks, but it's just going to shatter completely. You're not going to have any warning about it. So when it comes to that, it's very important to know about the test reports, because I've designed equipment using a yield strength of 800 megapascals, which is the sort of standard number for it. But what we got when we were looking at the test reports was 1150 megapascals. And then when we started looking further down, we could also see that the hardness was completely off. So it wasn't close to what we needed. We needed something that was a little bit softer. We couldn't have that hard of a material in the design that we were creating. So it's very important that we get the correct test reports and certificates with the materials that are delivered. And usually, when you're an engineer, it's usually somewhere else that's doing the fabrication and stuff. So they have to check the papers, and they usually send them to the document control department in your company, and they start checking the papers. And if they see something that, I'm not quite sure if this is what they're after, this is what my engineers are after, so then they'll maybe come to you and they'll say, could you look at these test reports and see if they're actually good enough? I'm not quite sure if they're good enough for you. And then you have to look through them and just verify if they're good enough or not. Also, internal controls are for making sure that we have satisfactory protocols, both for operations that we are doing and also for whatever equipment that we're using, stuff, so that everyone knows exactly how they're going to do it. It needs to be written down so that it's very clear. Then we get to risk analysis, or also safety and reliability analysis. But so in subsea production, we have very high requirements for the reliability and the safety level of our equipment, which is understandable because we are putting it down somewhere where we can't reach it very easily. So we need to make sure that, at least reliability-wise, we need to be able to trust the equipment, that it's going to work. So we're putting quite a lot higher requirements for reliability for subsea equipment than what we're doing for onshore equipment. Because with onshore equipment, you can keep inspecting it, and you can make sure that you replace it once it's starting to wear too much and starting to become less reliable. Then you just replace it with a new one. But considering how much work goes into replacing something subsea, you really don't want to do it unless you have to. And also, of course, for the safety levels, because if something goes wrong subsea, you might not actually notice it right away. So with the Kvitebjørn pipeline that had been dragged off by an anchor, the only reason that they realized that there was a gas leak there after a while was that they were doing regular inspections. So they were regularly going out there with a vessel and lowering down an ROV and just looking, seeing that everything was okay. And then suddenly one day when they came out there for their inspection, there was lots of bubbles coming up. And like Frederick said yesterday, if that had happened right beneath the rig, those bubbles have been coming up, that would have been flammable gas coming up underneath the rig. Someone is out there on the rig welding something or anything, then the gas is rising up there and it could be a huge explosion. So it's very important to have the safety in place. And the gear and equipment is very inaccessible when we are using it, because it's down on the ocean floor, which also means that all maintenance of the gear is very costly compared to onshore, and it's also very risky, because there is always a chance that something goes wrong when you're doing an offshore operation. So no matter how much you try to ensure that everything is going to go okay, everyone are only humans, so humans make mistakes, and even the smallest mistake can become a very large accident when you're offshore. So if you have equipment failure, or for that matter, when you are installing it or anything like that, there's some sort of mishandling so that you damage the equipment, it can have potentially very serious consequences. You can have very prolonged downtime of your operation. Your operation offshore can also have a prolonged duration. So you might have downtime with regards to production, and you might also have to pay for the crew being out there for a lot longer than what you originally planned. You might have emissions to the environment, and you might be basically putting both the personnel and the vessel in danger by having something go wrong. So usually the equipment has a lifetime of 15 to 20 years when they created. And if you're thinking about like a smartphone or something like that, you usually expect a lifetime of a couple of years. Maybe if you're lucky, your battery will hold a little bit longer than that. If you manage to switch out your battery, maybe you'll get 5 years out of your smartphone. If you're really trying to just use one smartphone and not switching it, usually people choose to switch it way before that time. But you could also look at a car. Expected lifetime of many cars is just 10 years. But many cars are much older than 10 years because they've been maintained well, so that they hold quite a lot longer. But the expected lifetime, at least from the manufacturer's point of view, is about 10 years, because their feeling is also that after 10 years, the safety equipment on your car is going to be so outdated that you would be much better off buying a new one, so that you should switch after approximately 10 years. But here we are talking 15 to 20 years as not being unusual, and I've even seen lifetime designs being done for up to 30 and 40 years. So some equipment gets quite a lot of attention when it comes to lifetime. And then just thinking about between 15 and 40 years of lifetime underwater with a lot of corrosion, you have to put very much thought into how you're going to design this in order to protect it properly. Most likely you're going to have maintenance intervals. For an example, every 5 years a vessel has to go out there and it has to replace all of the sacrificial anodes and maybe even do some extra work with trying to fix corrosion problems. But still, just by doing this every 5 years, you can have a lifetime up to 40. So it's quite different from what we're used to onshore. Onshore, it's so very easy to just replace your equipment when it starts failing. It's necessary to analyze the individual components and the entire system when you are both in the concept phase and in the engineering phase. So you might start wondering what's the difference between concept and engineering. So just to try to run a parallel to our For an example, for a module on a subsea template, so that module might have 20 years of lifetime. It might be that when those 20 years are up, it is still going to function way more than that, because usually they are very conservative when they set the lifetime of equipment. So usually it's going to last longer than those 20 years. But still, they need to, after 20 years, then they really need to have very frequent inspections just to check that nothing's going to go wrong. And preferably, they will switch it with a completely new module if needed. But then they have to start thinking about how many more years do we expect to have from this reservoir? Are we expecting 2 or 3 more years of production? Then we'll just maintain what we have, even though it's past its lifetime. We'll try to keep it in as good shape as possible. But if they see that with new technology, we can now extend the lifetime of this field with 20 more years, then they definitely just need to replace the module instead. We'll do a break, 20 minutes approximately. Right. We're continuing on with risk analysis and safety and reliability analysis. So we also run quantitative analyses, and quantitative means just that we have quite a lot to analyze, so we have lots of data. So usually it means a statistical analysis when we run it. So we put numbers to probabilities of failures within a given time frame. So we then use something called mean time between failures. So we try to calculate using statistics from previous failures to try to figure out how long are the intervals between each failure that we can expect. We also have qualitative analysis, and the qualitative one is more focused, to put it like that. So it attempts to locate the critical parts of the system, so that we can be more aware of what is the critical parts, what could cause those critical parts to fail, and what would happen if they fail, what would be the consequences. It also evaluates the need for backup or redundancy in the system. So if we figure out that we have a critical part in the system, and if that critical part fails, then our whole system just jams completely, nothing is going to happen, we get completely shut down by it, then we would like to have some backup there. So we would like to be able to route the system through another critical part so that we could continue production. Just to try to run a parallel here is to a pipeline. It's not really cost effective to have a backup when you're running a long pipeline. So that's why instead you have a place like the PRS base that can come out and try to repair it very quickly. And of course the critical point there will be a break somewhere in the line, so that they have to stop production. So as soon as there's a leak, they have to stop production, and then the PRS base has to be hooked up with it. But if they had two pipelines running in parallel in the same area, it would most likely only be one pipeline that had the leak. So they could then continue production in the other one. But it would mean twice the cost for putting down the pipeline. So it's not really a good thing to do in that case. But for an example, in a production system, if we're using a hydraulic cylinder to perform a task in a production system, and that task is very important, maybe the hydraulic cylinder is making sure that we are sorting our production line in the correct order, then it would be nice to have an extra cylinder there ready to take over the work if the primary one fails. So that then we can continue production while we replace the primary cylinder, because we have a backup one that is doing the job. They also evaluate for increased quality of a component. So basically looking at if we go for a stronger, better solution, will that help us? Do we then not need the backup? So going back to the pipeline, if we have thicker walls in our steel pipes, is that going to decrease the risk of having a leak in it? Most likely it's going to do that. So that might be something that they do. They put on a safety factor and they increase the wall thickness to a certain point, so that they have a stronger pipe to use. And for an example, with the hydraulic cylinder instead, you might use stronger materials, better quality seals, so that you won't have a leak in your hydraulic cylinder or anything like that. So that's also one way of increasing the quality. But usually when you're increasing the quality of your components, you're also increasing the cost. So it's always a balance point here, looking at how much can we afford in downtime and how much can we do we have to pay for quality. So we'll continue on with looking at probability in particular. And probability is the statistical evaluation of how often an event will occur during a certain period of time. So you would set, for an example, during a period of 10 years, if that's the lifetime of your equipment, how often do we think it is probable that something will happen. So that's going to give you the statistical basis for it. We also look at something called consequence, and that's an evaluation of how much damage an event can induce. So sometimes the damage is purely economical. You have downtime in production, so that you lose money, you're not making money. Other times it can be actual damage, something can blow up or something like that, so you get quite a lot of damage from it. So you have to sort of look at what's the consequence of the event. Then we also look at risk, and that is the combination of the probability and the consequence. So if there is a high probability of something happening, but there isn't really any damage done, not even economical damage done, if that happens, then the risk is very low. But if there is a very high probability and the damage is also high, whether it is physical damage or economical damage, then there is a very high risk. So you don't want to do that. And risk can be reduced by either lowering the probability, so making sure that this can't happen as often as we thought it might happen, or by lowering the consequence of the event. So making sure that, for an example, if we're talking about something possibly blowing up, then lowering the consequences might be to actually make the area around it more safe, so that no people are going to be in that area, no other equipment will be damaged by it if something goes wrong. That is also often why, for an example, gas bottles and stuff like that are stored outside. They're never stored inside. Only the ones that are in use are inside the building, and the rest are stored outside in a separate shed usually. Because if something happens to those gas bottles while they're being stored, they're not going to harm anything else than the gas bottles. They're not going to be inside the workshop when something happens. So that's one of the ways that you can lower the consequence of an event. But you can also lower both. So you can put in reactions to everything, so that you try to fix both consequences and the probability of it. Yeah. Well, then you have to look at the past data, and you have to basically look at the cause of the events. So the probability is how often the event occurs. But the probability doesn't tell you anything about why it occurs, right? It just tells you how often it is. So then you have to go into each separate instance and you have to look at it. For an example, if you have a certain event that happens and you figure out that one of the causes is that the workers are being a little bit sloppy and they're not following the routines that they're supposed to do, and when that happens too many times in a row, then this event occurs, for an example. Then one thing could be to have much stricter routines so that you avoid causing these events. So that's one way of lowering the probability of it happening. And there are also other ways. For example, if it's purely equipment based, that the equipment just simply breaks down after a certain amount of time, then it could be to put in servicing intervals that are more frequent than the breakdowns, so that you sort of catch it before it breaks down. So that's also one way of lowering the probability. So one of the ways that we analyze this is a so-called rough analysis or hazard identification. It's also shortened down to HAZID for hazard and identification. And it's implemented early in a project. And it can be used for both equipment and also for system design, and also when you are developing operational procedures. So whether you are designing equipment or you're designing an entire system, or you are just trying to put down how you're going to use the system and do the work. And it quickly identifies weak points in a construction or even unacceptable risk in an operation. So, for an example, if you're doing a lifting operation and you use a hazard before or when you start planning the lifting operation, then you suddenly see that we're going to be lifting this stuff over a crowd of people. Well, we don't want that. If something falls down, then it's going to land on a crowd of people. So that's a weak point or an unacceptable risk. Then we have to make sure that we have to make that crowd of people move away when we're doing the lift, so that we're lifting over a bare ground. So it's just going to fall down and not do any injuries to people. So that's one way of quickly identifying stuff. So one example we have is for preparation. You gather the necessary information about the procedure or about whatever it is that you're going to construct. You divide it into main activities or keywords. So basically you sort of start dividing it up. So if it's a lifting operation, one of the keywords might be lift, so vertical lift. That might be one of the keywords. One of the other keywords might be horizontal translation. So when after you've lifted it up, then you are moving it to the sides. One of the keywords might be fall. So if something falls down, what's going to happen? So you start putting in words like that, and you start looking for what could happen with these words. And each of the keywords, they represent a risk. So like here, a loss of load from a lifting hook, loss of electricity. If you're running an operation that is dependent on electricity to run, something could go wrong if you lose your electricity and equipment stops, for an example. If you're talking, for an example, about divers, if they suddenly lose electricity to the diving system, are they going to be able to maintain pressure in there for the divers, or is it going to be dangerous for them? Then you implement the stuff that you've figured out in the preparation. And when you are implementing it, all of the disciplines should be represented in your team. So even all the way from the engineers that are designing it to whoever is going to operate it, and everywhere in between. If it's equipment, whoever is going to fabricate it also needs to be in there. The document control people need to be in there. Everyone that's involved in the project needs to be represented in the team. So not all of the people need to be there, but one from each discipline needs to be there at least. Then the hazard team, they go through every activity or keyword and identify critical events that could lead to a consequence. And for each of the critical events that they identify, they also figure out the cause of that event, the consequence of it, and possible preventative measures. So for an example, if we were lifting something up and moving it above a crowd of people, a preventative measure would of course be to have the people removed before we start the lifting operation. So that's some of the stuff that they're looking at then. It also includes evaluation of the equipment that is to be used. So then you would evaluate the crane that's doing the lift, the hook, the wire, everything is being evaluated. And also looking at external factors, so wind and waves. If it was a lifting operation on land, it would only be wind. So you would, for an example, set a requirement that we would not perform this operation with winds higher than 8 meters per second, for an example. At shore, you would have to put both wind and waves into account. So you would have to say a significant wave height of maximum 4 meters and a wind speed of maximum 10 meters per second or something like that before you do the lift. So that you can't do the lift if any of those requirements are exceeded. And then you also need to document it afterwards, because it's one thing to just do all of this before you start planning whatever it is that you're going to do, but you also need to put it down on paper so that you can go back and see what was it that we talked about in this meeting. And usually a risk table is used. So they put up a table where they put up all of the risks and all of the consequences and causes and stuff like that. So it might look something like this, where we have a risk of toxic emission in a facility. And the cause might be a cylinder leakage from gas storage. So that might be one of the causes for this toxic emission. And the main effect would be that we would have a large emission, and it could lead to a serious accident. And a preventative measure could be a warning system. So if you have sensors that are able to detect this toxic gas or whatever it is, then they can do a warning. Whenever it gets a readout on the sensor, it's going to set off an alarm system. It might also be to minimize on-site storage, so make sure that this cylinder isn't completely full, or that it's much smaller than what it is right now, as small as it can be. It could also be to develop a procedure for inspecting the cylinder. So if you're inspecting it often enough, you would most likely be able to catch whatever damage it is that's been done to it in order to make it leak. Whether it is just wear and tear with sealing parts being worn down and starting to leak, or whether it is corrosion that causes the leak or whatever it is, you might be able to catch it doing proper inspections. Another cause could be that the gas is not entirely used up in the process. So this is in a facility that is doing something with this gas. And if it's not using up all of the gas that it's supposed to use, then you're going to have a large emission that can lead to a serious accident, so the same as above. And one way that you could prevent this is to make sure that you can collect all of this excessive gas, so that it's not going to be just released into the environment and become a hazard. So this is one of the ways that you can use the hazard system. Another system is called failure mode and effects analysis. And it highlights the effects of failures in technical systems. And it starts off with each individual component, and then it sort of starts looking at them in sequence in the system. So what happens if this one fails? What happens then with the rest of the system? And it decides which failures are possible and not possible, because usually in a system like this, you are going to basically just be throwing out whatever comes into your mind when you're looking at your system. So it might even be as far-fetched as a meteor falling from the sky and crushing the equipment. So it might be that far-fetched. It's highly unlikely. So it's something that's not going to be possible, basically. It is possible, but it's such a very small probability that you won't really be taking it into account. It evaluates what will happen if the failures that are possible occur. So basically the failures that we can do anything about. We can't do anything about a meteor falling from the sky. That's impossible. But this means that we go through all of the possible failures in the system, and that's the entire system, and it's being done in a systematic manner. So you sit down with the sort of charts over the entire system, and you start just looking at each component, and you follow the entire system from start to end and go through everything. And here they also use tables to keep an overview of the work that they are doing. And the tables might look something like this, where you have a description of a certain functional unit inside the system. So you're down to focusing on one unit. And you have some designations and numbers to identify it, the function of the unit, and also the operational condition and phase. Then you have different descriptions of failures. So the failure mode of the unit, the failure cause or the mechanism of the failure, failure character, background for failure, failure development, failure frequency, and classification of failure. So you're sort of systematically putting up how it's going to look. and how the failure is being detected. So it might be that an inspection uncovers it. So if it's noticed or if it's failed to be uncovered in an inspection and stuff like that. So you're just basically putting up what can be discovered in an inspection and what is highly unlikely to be uncovered. For an example, corrosion inside a gas tank. You're not going to be able to, most likely not going to be able to detect that with just a visual inspection on the outside. Because if you can see the corrosion then you already have a leak. If you're doing an NDT from the outside, then you might be able to detect it. Or if you have some way of putting a camera inside a tank so that you can actually have a visual inspection from the inside. So it sort of looks at different ways of detecting the failure. It also sets up the effects of the failures, both on the functional unit itself, on the system, and then on the totality, including the external environment. And also, it looks at possible reductions, both of sort of the cause of the failure and the effect of the failure. How can we reduce everything? So the best thing is, of course, to reduce the cause of the failure, to make sure that the failure doesn't happen. But just in case, it might also be wise to put in some measurements that are going to reduce the effect also of the failure. So we have an example of failure mode and effects analysis. So we have this system set up where we have a fluid vessel, which is basically this tank here. And it acts as a buffer of the flow between the source that is up here and the consumer that goes out here. So basically, if we have a sort of intermittent flow coming, and we have we could also have a steady flow, and then just every now and then the consumer is using part of the fluid. It could also be that the consumer is using a very small flow of the fluid at all times, and then we have a very large flow coming every now and then from the source. Either way, how the system works, we need to gather up some fluid in this tank. And the problem is that the way this has been designed and constructed, the water can overflow the edges of the vessel. And we don't want that, or it's not necessarily water, it's a fluid, so it could be anything liquid. And we have 3 valves in place to avoid overflowing. So we have 2 shut-off valves from the source in order to make sure that we don't get any more fluid flowing into the vessel. And we also have the drain valve, so we have the possibility of draining out what's in the vessel. And we have 5 functional units with necessary signal transfer between them. So 3 of the functional units are the valves. So the drain valve and the 2 shut-off valves. And we also have 2 sensors that register the amount of fluid that is in or basically the fluid level in the vessel. So the sensor that is named LSH, it gives a signal to close the V1 valve if the fluid level becomes too high. So if the fluid level comes too far up here, then LSH tells this one to close. Then the LSHH sensor, it signals to V2 to close and V3 to open if the fluid level increases even further. So it's, for an example, if this one is jammed slightly open so that we still have a flow coming, then this one is going to, we're going to get an increase in fluid flow, so this one is going to react, close that one, and it's also going to open that one to make sure that we get a lower level of fluid. And the flow rate that we can get through the drain is larger than the flow rate coming from the source. So either way, if both of these 2 fail to close, so that we still have a flow rate coming into the fluid, as long as we get this one open it's going to drain faster than it's filling up. So that's the last fail-safe that we have in this case. So if we try to analyze the LSH sensor, it's going to have two failure modes. And one is that the signal is not being sent when the fluid rises above the given limit, so that it simply fails to register that the fluid has risen above the level. Or it might be that it's sending a signal, but the fluid hasn't risen above the level. So the fluid is in a normal okay level, but the sensor is misinterpreting it and saying that, whoa, we have too much fluid here, so I'm shutting down the V1. Both of those are failures because they're going to interfere with our process at the consumer side. Because if it shuts down when the fluid level is okay, then we're not going to get more flow in, and the fluid level is only going to keep sinking as the consumer is using it. So in the end, it's going to use up all of the fluid. And also the problem is that it's going to start overflowing if it's not stopping. Of course, we still have this one, but right now we're only analyzing LSH, so we're not looking at what LSHH will do. So if LSH, the function of LSH is that it's a level switch, and it sends a close signal to V1 when the level rises too high. And the failure mode is that it doesn't send a signal when the fluid level is too high. That means that V1 does not close, and the fluid level can rise to a very high level. We don't have any corrective measures for this, and the failure frequency is estimated to be 1% of the total amount of events. So for just 1% of the times that it sends the signal, it's going to fail sending it. So if we have 100 events where LSH needs to close down V1, one of them is probably going to be a failure. So then we have to sort of look at how often does LSH actually shut down the V1 sensor, the V1 valve. Yeah.
Does the sensor recognize when the fluid is completely drained out at the time and restart the system?
No, we don't have any sensors for that. So that's another thing. If we had done this example only focuses on the LSH sensor, but if we had done the entire system, we would have seen that we should have something looking at the opposite one also if we are emptying the vessel completely of fluid. So that's one thing that we have to keep in mind also, that it's not one of the problems with methods like this is that you get so focused on details that you sort of forget the big picture of it. In this case, they put a grade on the failure effect of 3. So then we have the other failure mode, and it's when it sends a signal when the fluid level is not too high. So V1 closes when it should not close, and the fluid flow is stopped. And this happens approximately one time every year. So that once every year, this is going to happen. And they put a failure grade of 1 for it. So in this case, they've not put that much thought into this one. It's not that important. So most likely, it's not that bad if the fluid vessel runs out of fluid. It's going to not be a huge problem for the rest of the system. And in this case, they've used the grading systems of using numbers, so the numbers pertain to something. In many cases, you just use, for an example, critical, and that's if the failure reduces the functional ability of the system beyond acceptable limits. So something is going to happen to the system, and we're, for an example, going to have downtime. We're not going to have more production. That's unacceptable. So that's going to be a critical failure. A failure, or it creates unacceptable conditions, either operational or safety-wise also. A failure could also be a great failure instead of a critical one. And if it's a great failure, it's going to reduce the functional ability of the system beyond the acceptable limits, but it can be maintained or controlled by separate measures. So it's not going to create unacceptable conditions safety-wise or anything like that. It's not going to be dangerous. You can control it, but it's unacceptable to normal production to have it like that. You could also have a failure grading of small, and then the failure doesn't really affect the functionality of the system. So that for an example, I would guess that if the fluid vessel is completely emptied, then that's just a small failure in this case. DNVGL also has some grading of failures that they propose to use, and then they use A1, A2, A3, B1, and B2, where we start off at the top, and failure effects that do not cause loss of any primary functions. And then as we move downwards, they are getting more and more severe. So, and we get down to B2, failure effects that cause damage to equipment in such a way that it cannot be repaired by the regular personnel. So then you actually have to have outside personnel come in to fix it. So there are limitations to failure mode and effect analysis, and it can be very work intensive, because if you have a large system, if you look at, for example, Kårstø, if they're going to run failure mode on Kårstø, there are probably thousands of valves in Kårstø and equally as many sensors, most likely. So if they're going to go in for every one of those and sit down and look at all of the possible failures and effects, it's going to be a very work-intensive job to do. It also requires in-depth knowledge of the system functions and also the environmental and operational conditions. So you really need to know the system that you're analyzing in order to see what's going to happen. You can't just one of us can't just come into Kårstø and do a failure mode analysis, because we don't know what's going to happen if a certain failure goes on. It does not uncover critical combinations of failures, and this is an important one. So for this one, we were looking at LSH. We could also start looking at the other sensor that was supposed to be the backup of the LSH, but it doesn't really tell us anything. What if both of those fail? So what's going to happen then? Then the vessel is going to overflow if both of those fail. So it doesn't really look at the big picture of it. You can have too much focus on technical failures also, meaning that you overlook human contributions to failures. For an example, a technician that has wrongly opened another valve in some other part of the system, that might affect the part that you're analyzing. It can also be poorly suited for systems with high redundancy. So if you have much backup systems in order to make sure that you're never going to completely shut down production because you have so many backups. But that means that you have to go through all of them and look at every single component also. So it's going to be even more work intensive. And it's also not guaranteed to uncover all of the critical unit failures. So it's sort of not all that good in that department, and it focuses on unit failures, not the cause of the failures. So we were looking at LSH having two different types of failures, but we didn't look at why would it have those types of failures. For an example, the failure being that when it shut down the valve when the fluid level was okay. That could be as simple as if it's a floater in there, so it's an element that's floating on top of the fluid, and that's what's triggering the sensor. It might just be that the floater has gotten jammed in a high level, so that it's actually not floating anymore. It's being lifted above the fluid, so that the sensor thinks that it's the fluid level is way too high. That's actually something that happens every now and then in cars for the windshield. What's it called? The windshield fluid, the one that you basically just wash the windshield with on the car. It has a floating sensor in it usually. So it has a floating element, and it tells what the level is. Sometimes those fail, and the car thinks that you have enough of the fluid while you've actually used everything. Then you're suddenly out there driving on a dirty Norwegian winter road. Your windshield is getting more and more brown, and you almost can't see through it, and you have no fluid to wash it away. So that would be a critical failure, basically. You would have to stop at the closest gas station and buy some more fluid. But it focuses on the failure, yes, not the cause of the failure, but it is still a very effective way of doing technical analysis. So just analyzing the technical stuff in a system. It's very good at doing that. So if you have a fairly small system with not too many components, and you want to figure out the technical aspects of having failures and stuff, it's a very good way of doing it. We also have something called fault tree analysis, and it's an incident-oriented logical diagram. So it uses a lot of the logic that you used in the second math course that you had. So the and, or operators, if, else operators like that. And if it is performed correctly, it is actually possible that you can uncover combinations of errors that you previously didn't know about. And it can also detect weak parts of the system when you're doing this fault tree analysis, because this one is looking at the entire system and what the effects are going to be. So it can be used both qualitatively and quantitatively. And it creates an overview of the logical causes of a chosen incident. It can be used both before an incident as a preventative measure. So when you're planning a system, for an example, you can use it to try to figure out the best way of designing the system. But it can also be used after an incident to figure out what really happened. So just to do an extreme example, the Deepwater Horizon incident in the Mexico Gulf. You could use a fault tree analysis afterwards to try to figure out what exactly went wrong to cause that accident. It shows the correlation between unit failures and the system failure, so which is the top incident. So in the Deepwater Horizon, it will be the whole rig blowing up, basically, and a huge environmental disaster. But somewhere in that tree, there is going to be one single unit failure that started off all of this chain reaction that went all the way to the top of the tree. And it utilizes the and or symbols equivalent to the Boolean logic that you know from the second mathematics course, and also that is used in programming. So often used in Excel spreadsheets if you want to have some extra functions in there. If one or several parallel branches of the entry incidents fail, the system can still function. So much like a steel wire rope. If you have a tree that you have a top incident, but it also has several branches going down to different failures here in the system. You could have a failure over here, and it's going to sort of wipe out this one, but the other branches will still work because they are not directly connected to that side. So you sort of have several strands of rope that can be snapped before everything breaks. But if you only have one branch, so if everything is in a series downwards, then if you have a failure up here, then it's going to be like a steel chain. So if you snap one of the chains, the steel chain isn't a steel chain anymore. You don't have one single length, you suddenly have two lengths of steel chain. And the way they use it is using different symbols. So they have this one as an OR gate. So this means that the incident above it occurs if at least one of the incidents below occur. You have the AND gate that means that the incident above the symbol occurs only if all of the incidents below it occur. And also coincidentally, they have to happen at the same time. You have entry incidents, so they're used all the way at the bottom of the tree. So all the way at the bottom, those are the unit failures. So if a single unit fails, that's an entry incident. Then you have a failure incident. It is explained by other failure incidents. So it's basically an effect of other entry incidents. Then you have failure incidents that are not analyzed all the way to the bottom of the tree. So you're stopping somewhere in the branch. You're not doing it all the way down. And then you also have the possibility of transferring in and out to other trees, but then you're going into really complex, huge trees. So this is an example from the previous example we had. So now we're doing a failure tree on it. It's still the three valves, V1 not closing, V2 not closing, and V3 not opening. Those are our main failures here. And we will have overflowing of our fluid vessel. You can see here we are using an AND operator there, which means that V1 is not closed, and V2 is not closed, and V3 is not opening. Then we're going to have overflowing. And then we can go down to V1 here, because we know this part. We did this in the previous example where we looked at it. V1 is not working. That could be one of the reasons. So the LSH sensor is working, but V1 is not working, so it's not actually closing. And we have an OR here, so it's either that one or that one. That could make it not close. And here we also have LSH not sending a signal and V1 not receiving a signal from LSH. So here we are also taking into account that not only is the sensor not sending the signal, but it could also be a break in the wire going from the sensor and to the solenoid on the V1 valve. So if there's a break in the wire, the signal won't arrive. So the sensor is still saying that close down, and it's not closing down. So that could also be a possibility. But here you can see we've set up all of it so that we can look at everything that's going to happen. If we have a larger failure. So here we can sort of see more of the entire path of one failure. What's going to happen if that one failure happens? What's going to happen then? And we can see that if only we have a failure here with LSH not sending a signal, it's going to cause this failure, V1 not closing. But so long as everything else works, then these two are going to work, and that means that we won't have this one up here, because this one is dependent on having all of these three happening at once. So I think we'll stop there. We'll continue with hazard and operability study next week on Tuesday for the last lecture. So I think we have one or two more risk analysis stuff, and then we'll start looking a bit at corrosion in subsea systems. So I'll see you tomorrow for the hydraulics. Oh yeah, and I